Hello and good morning to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will discuss a very important concept in operating system that is called as process synchronization and deadlock. To begin with, let us try and understand what process synchronization is all about. As we all know, a typical computer system may have in it several cooperating processes. Here, cooperating processes refers to a set of processes that interact with each other either through shared logical address space or through shared data files in order to realize the very objectives of a computer system. Again, I'm repeating it. A typical computer system may have in it several cooperating processes, where cooperating processes refers to a set of processes that interact with each other either through shared logical address space or through shared data in order to realize the very objectives of a computer system. In regards to the very nature of organization of the cooperating processes in a computer system, cooperating processes may affect or may get affected by the execution of other processes that are there in a computer system. Cooperating processes, as I've already said, may share among them logical address space, or they may share among them data files in order to perform operations. The execution of the cooperating processes in a computer system may be attempted at discrete point in time or may be attempted concurrently. Whenever the cooperating processes are attempting to execute concurrently, they may need an access to the shared data or to the shared logical address space concurrently. So here, concurrent basically refers to attempting to execute at same point in time. Now, there exists a typical problem with concurrent execution. Concurrent execution calls for concurrent access to shared data, which may result in data inconsistency. Data inconsistency basically refers to hampering the integrity of the data that is there in the computer system. Therefore, it is very essential for all of us to plan the execution of the cooperating process in a manner that it preserves the consistency of data. So therefore, orderly execution of these processes is very essential for ensuring data consistency. This process of sequencing the execution of cooperating processes in a computer system is called as process synchronization. So the process synchronization is the art of sequencing the processes that are there in a computer system. Now let us try to understand the same with the help of a very simple example. So here I've taken two instances, an instance where cooperating processes utilizes exclusive resources and an instance where the cooperating process utilizes shared resource. We will try and understand how execution of cooperating processes is to be done whenever the cooperating processes utilizes shared resources. So let us discuss both the instances. Now here, for simplicity, I am representing the processes with the help of 5 trains. So these 5 trains represent 5 different processors in a computer system. So in the first case, or the first instance, all of these 5 processors have their exclusive resources. So these 5 trains have 5 routes, where each route exclusively belongs to each of the trains. So in this scenario, the execution is pretty simple. So the 5 trains needs to make use of these 5 routes in order to perform the task of traversal. So these 5 train utilizes these 5 routes in order to perform traversal. Now in the second instance, again what we have is we have 5 trains representing 5 processes, but here we have only a single route. So now the task becomes complex. So here the activities of these 5 trains are to be coordinated in a manner that they efficiently and effectively utilizes the single route. So in order to ensure that these 5 trains is capable of utilizing the single route, we need a coordinator. So here the coordinator is the route master. So the route master is responsible for coordinating the traversal of these 5 trains utilizing the single route. Now how does he do it? He does it with the help of a simple variable, that is a flag or an entity. So for now, let us consider it's an entity. So the route master coordinates the task of traversal of the 5 trains utilizing the single route with the help of an entity that is called as a flag. Now you must have observed, while traveling through train, this flag that is used by the route master has 2 colors. 2 colors which are red and green. Red signifies you need to wait. There is someone else utilizing the route. And green signifies that you are free to use the route. So red indicates you need to wait, green indicates you need to use. So I can say that red indicates wait and green indicates signal to use the route. So what does the route master do? The route master first indicates to all the trains that the route cannot be used because the route is shared and proper coordination has to be done. So once all the trains know that there has to be coordination taking place for utilization of the route, so they will wait for the route master to signal them to use the route. So now what does the route master do? The route master changes the status of the first train. So he shows the signal to the first train to utilize the route. So once the first train receives the signal to utilize the route will be utilized by the first train to perform traversal. Now likewise, the route master will then signal the second train to use the route. Further, the route master signals the third train to utilize the route. Likewise, the route master signals the fourth train to utilize the route. And eventually, the route master signals the fifth train to use the route. So this is the way how the route master coordinates the utilization of the route among the various trains who are utilizing a shared route. So this coordination is done with the help of a very simple variable or very simple entity, that's flag, which may have two colors, that is red and green, red indicating wait and green indicating signal. So whenever I want the train to wait, I will execute a function wait, and whenever I want a train to move, I will execute a function signal. So signal on the entity, that is flag, or on the variable, that is flag. So this variable that is used by the route master in order to coordinate the activities of various trains utilizing a single route is called as a semaphore. So semaphore is a coordination variable used by the route master in order to facilitate use of a shared resource or a shared route by multiple trains. Now let us try and understand semaphores in a greater detail. Now semaphore, to begin with, was proposed by a Dutch scientist called Edgar Dijkstra's. So Edgar Dijkstra's proposed a technique for managing concurrent processes for mutual exclusion problem called semaphore. So it's a general knowledge question as well. So Edgar Dijkstra's proposed a technique for managing concurrent processes for mutual exclusion problem called semaphore. Now semaphore, as we have learned, is a status variable that is shared among various cooperating processes for enabling processes to decide on execution of its critical section utilizing shared resources. Now, as of now, it may be difficult for you to understand, but just remember that a semaphore is a status variable that is shared by all the cooperating processes that belongs to a computer system, which enables them to decide whether or not to execute utilizing shared resources that are there in a computer system. So a semaphore is a status variable used by all the cooperating processes in a computer system to decide on whether or not to execute utilizing shared resources that are there in a computer system. Now semaphores, as understood, it can be of two types. The first type is called as a binary semaphore. The second type is counting semaphore. So each of this type of semaphores have their own specific use. Binary semaphore, as the name says, is a semaphore that can have two values, either 0 or 1. So binary semaphore is a semaphore that can have only two values, that is either 0 or 1. Whereas counting semaphore is a semaphore that can have any non-negative integer value. So based on the purpose of the use, we can put into use either binary semaphore or we can put into use counting semaphore. So we will try to understand binary semaphore and counting semaphore with the help of an example at later point in time. But for now, just remember that there are two types of semaphores, binary semaphore and counting semaphore. Binary semaphore can have two values, whereas counting semaphore can have any non-negative integer value. Now, as learned earlier, there are two standard operations defined on the semaphores. The two standard operations are wait and signal. Correlating to wait and signal in the previous example, here we are articulating that there are two standard operations defined on semaphore, that is wait and signal. So wait is executed in order to make the process know that you need to wait because there is some other process that is already executing, and signal is used in order to let a process know that no other processes are executing and it's your turn for execution. So wait and signal are two functions that performs operation on semaphore in order to make the process know whether or not to initiate the execution. The modification to the semaphore values through wait and signal should be done indivisibly. So this is very much important. The modification to the semaphore value through wait and signal should be done indivisibly, implying when one process is modifying the value of the semaphore, no other process in a computer system should be allowed to modify the value of the semaphore. So this is called as indivisible execution. So again, I'm repeating it. The modification to the semaphore value through wait and signal should be done indivisibly, implying when one process is modifying the value of the semaphore, no other process should be allowed to modify the value of semaphore, because as we have learned that semaphore is a value that is shared among all the cooperating processes that are there in the computer system. So whenever one process is modifying the value of semaphore, no other process should be allowed to modify the value of the semaphore. Now let us try to understand the significance of the wait and the signal function. The wait command, which is also represented by P, decrements the value of the semaphore by 1. Again, I'm repeating it. The wait command, which is also represented by P, decrements the value of semaphore by 1 only if it is positive. If the value of the semaphore is negative or 0, then no operation is performed. So here you need to remember that wait command, which is also represented by P, decrements the value of semaphore by 1 if it is positive. In situation if the value of semaphore is negative or 0, then no operation is performed. What is the significance of wait is that entry to the critical section is controlled by the wait operation. Again, this is very important. Entry to the critical section is controlled by the wait operation. So wait command represented by P decrements the value of semaphore by 1 if it is positive. In situation if the value of semaphore is negative or 0, then no operation is performed. The significance of wait is that wait is used in order to decide on the entry to the critical section. Now, why it is called as P? Here, P refers to proberen. Proberen in Dutch basically refers to test, or to the act of testing. So here, before entering into critical section of a particular process, we will test whether the shared resources that are there in the computer system are free or are being utilized by some other process that is there in the computer system. So here P refers to proberen, that is the act of testing. The testing of whether the resources are being utilized by some other process or it is free. Only in situation if it is free, then what we'll do is we'll make the process execute its critical section. Otherwise, the process has to wait for the current process to get over utilizing the shared resources. So wait command Again, I'm repeating it. So this is very much important operating system. So the entire synchronization takes place with the help of these two functions. So it is very important for us to understand the significance of these two functions. So wait command represented by P decrements the value of semaphore by 1 if it is positive. If the value of semaphore is negative or 0, then no operation is performed. Entry to the critical section is controlled by the wait operation. Now let us try to understand the signal command. The signal command represented by V increments the value of semaphore by 1. Exit from a critical section region is taken care by signal operation. Again, I'm repeating it. The signal command increments the value of semaphore by 1. Exit from a critical region is taken care by the signal operation. It is named V because V in Dutch represents Verhogen, where Verhogen represents the act of incrementing or incrementation. So that's the reason why the wait and the signal command is also known as P and V. So mutual exclusion of semaphore is enforced with the help of the two functions, that is P and V, or wait and signal. So wait and signal is used in order to synchronize the activities of various cooperating processes that are there in the computer system. So wait decrements the value of the semaphore. If it is positive, if it is negative, it does not perform any operation. Signal increments the value of semaphore by 1. So entry into the critical section of a process is controlled by wait, whereas exit from a critical section of a process is controlled by signal. So wait and signal are the two synchronizing functions used on semaphore for coordinating the activities of various cooperating processes. Now, how does it actually work? So before deciding on whether or not to initiate the execution of a business process or a cooperating process, the cooperating process needs to execute the wait function. Based on the value of semaphore, the wait function lets the cooperating process know that whether it can or whether it should not initiate the process of execution. So consider a situation when the value of semaphore is 1. So when the value of semaphore is 1, then the cooperating process executes wait. The wait then decrements the value of the semaphore to 0, signifying that now no other process will be allowed to use the shared resource, and the privilege is exclusively given to you, and now you can perform your desired operation. And then eventually, when a cooperating process performs a desired operation, it has to let the other processes know that the resources are now free. So what does it do? It increments the value of semaphore. So that is the way how it actually works. So this is the very purpose of wait and signal and the semaphores. As we have already learned that semaphore is a shared variable that is shared among all the other processes that are there in the computer system. So wait and signal works on the shared variable to let the business processes know whether or not they can initiate the execution of their desired behavior. Now, as shown here, wait, what does it do? It, just see here, what we have is we have a while loop. So while s is less than equals to 0, so what it will do, until this condition is satisfied, it will keep on waiting. Moment the value of s becomes greater than 0, it will decrement the value of s by 1 and let the business process perform operation. So what does while wait do? So wait, we will first wait until unless the value of semaphore is less than equals to 0. Moment it becomes 1, it will decrement, the condition will not be satisfied, then it will come to the very next statement, that's s minus minus, so it will decrement the value of semaphore and let the business or the cooperating process perform its operation. Now likewise, signal. So what does signal do? Signal will simply increment the value of semaphore by 1, signifying the exit or releasing the use of the shared resources. So this is the way how wait and signal function basically performs its operation. So this is very important for all of us to understand, because the entire synchronization of the cooperating processes in the computer system will be making use of the wait function and the signal function on the semaphore to perform operation. Now, as discussed, semaphores are of two types. We have binary semaphore and we have counting semaphore. So binary semaphore can take two values. It can take either 0 or it can take either 1. Binary semaphores are also known as mutex lock, as it is used for mutual exclusion with initial value as 1. So binary semaphores are semaphores that can have two values, which is either 0 or 1, and it's also known as mutex lock, as it is used for mutual exclusion with initial value as 1. Counting semaphores are semaphores that can take any non-negative integer value. Counting semaphores are semaphores that can take any non-negative integer value. So here I have taken up an example for counting semaphore. So consider that there are three processes A, B and C requiring resources. So there are three processes A, B and C requiring resources, and there are two instances of resources R1 and R2 to be shared among them. So there are three processes and there are two resources that are to be shared among the three processes. So here what I'll do is I'll set the value of semaphore to 2 because there are two resources. So here the value of semaphore is set to 2 as there are two instances of resources. So here, as the processes are arranged in the sequence A, B and C, so first A will get the resource. So once A gets the resource, the value of the semaphore will be decremented by 1. So the value of semaphore becomes 1 from 2. Now after that, B is allotted the other instance of resource. Now the value of semaphore is decremented by 1 further. So now the value of semaphore becomes 0 from 1. Now once the first instance and the second instance of the resource is allocated to A and B, the value of semaphore becomes 0. Which implies that now C has to wait for A or B to release the resource after completing their execution. Only then it can be assigned to C. So that is the way how counting semaphore is used. So here again I'm repeating it. So here there are three processes and two instances of resources. So we are initializing the semaphore value to 2 because there are 2 instances of resources. So once A is allocated an instance, semaphore value is decremented by 1. Further, when B is allocated an instance, the semaphore value is further decremented by 1. So now the value of semaphore becomes 0, which tells C that C has to wait because the resource has already been allocated to A and B, and it can start its execution only when the resource is being released, will be released by A and B. So that is the way how counting semaphores are used. So here we have learned that there are 2 types of semaphores, binary semaphores and counting semaphores. Binary semaphores can have 2 values, either 0 or 1. Counting semaphores are semaphores that can have any non-negative integer value. So based on purpose, we can make use of either binary semaphore or we can make use of counting semaphore. Now let us go through some of the advantages of semaphores. So the first advantage of semaphore is that it allows only one process to enter its critical section, enabling mutual exclusion. So we'll come to critical section in the next portion of the curriculum, but for now just remember that critical section is a piece of code in a process that calls for its execution. So a semaphore allows only one process to enter its critical section, enabling mutual exclusion. Semaphores allows for optimal utilization of resources. So only those processes that are allowed to enter its critical section will be utilizing the shared resources. So semaphore allows for optimal utilization of resources. Third one, the most important of the advantage of semaphore is that semaphore are implemented in the machine independent code of the microkernel or microkernel part of the operating system. So they are machine independent. So it's a very simple code which there is very simple code which increments and decrements the value of semaphore, and these are implemented at micro or machine independent code of the microkernel. So they are machine independent, so they can run on any machine. Now let us go through some of the disadvantages of semaphore. So as we have learned that there are 2 functions, wait and signal, that act on the value of semaphore. It is very important for all of us to ensure that there is proper sequence maintained in the execution of wait and signal, which implies that wait has to be executed first, followed by execution of critical section, then followed by execution of signal. Any disturbance in the orientation of execution of wait and signal would make the entire process of synchronization very complex. So semaphores are complicated so that wait and signal operations must correctly be implemented. Now semaphore leads to loss of modularity as it disturbs the structural orientation of the computational system, because every time whenever a process wants to enter its critical section, it has to execute, wait, and upon completion of execution of critical section, it has to execute signal. So every time a process wants to perform its operation, wait and signal has to be executed. Definitely it disturbs the modularity of the overall program orientation in a computer system. And the third disadvantage is that semaphore may lead to priority inversion. So we'll come to priority inversion in the later classes. But for now, just remember that semaphore may lead to priority inversion. So in today's class, what we have learned about is we have learned about what is process synchronization. We have learned about the act of executing cooperating business processes in the computer system concurrently. What is the problem in concurrent execution, and what is process synchronization? Then we try to understand process synchronization with the help of two examples where we have considered processes executing utilizing exclusive resources and processes executing utilizing shared resources. Then we have learned about the significance of wait and signal function that acts on the variable that's called as flag. Then we have learned about how it actually performs its operation, or how does the coordination take place. Then we've learned about semaphores in greater detail. We've learned about what is semaphore, how does it help in executing cooperating processes. Then we learned about the different types of semaphores. Then we discussed the standard operations that are there defined on the semaphores. And then we learned about why it is important to have the wait and signal perform its operation indivisibly. Then we learned about the wait and signal command in a greater detail. We also came to know about the nomenclature that is used for wait and signal. So P is the nomenclature used for wait and V is the nomenclature used for signal, representing proberen and verhogen, where proberen in Dutch refers to test and verhogen in Dutch refers to increment. And then we've learned about how wait and signal enables us to synchronize the operations of cooperating processes in a computer system. Then we have also learned about the implementation of wait and signal. Then we learned about the types of semaphores in greater detail. So where we learned about binary semaphore and cooperating semaphore, and we tried to understand the same with the help of an example. Then we moved on to the advantages of semaphores and the disadvantages of semaphores. Now, in the next class, we will be proceeding on with critical section. Till then, thank you very much and have a very good day.